All right, today we're going to cover chapter 7 of Strogatz about limit cycles. Now, what a limit cycle is it's essentially a closed orbit in phase space, in two-dimensional phase space. So we start at some initial condition, and then we kind of let the solution flow out throughout time, and eventually it returns back to its initial starting point. And due to the single valuedness of our differential equation, okay, um, once we return to this starting point, we're going to have to repeat the exact same behavior throughout time, and so the solution will be periodic and will continually oscillate through this limit cycle. Now, the other requirement for something to be a limit cycle is that it has to be isolated. So essentially, it can't be neighboring like other limit cycles that are infinitely close to it. Okay, and so remember that in the linear case, the only time we have periodic solutions is if we have like a center, okay? So try to remember when do we have a center? It's when the eigenvalues of our matrix x dot is equal to ax, when these eigenvalues are purely imaginary. And then we get centers. So periodic solutions that look like this. But these periodic solutions are not considered limit cycles because they're not isolated. So any limit cycle, you can move an infinitesimal distance, and you'll find another limit cycle right next to it, neighboring the periodic solution. And so, in fact, excuse my language here, but in fact, we don't have any limit cycles um, in linear systems. We need that's a purely nonlinear phenomena. Okay. And so this whole kind of chapter is about identifying um, when limit cycles do exist and when we can rule them out. And then once we kind of figure out a few strategies for doing that, we'll look at some different types of oscillators and different types of oscillation processes that are common in science. So first, let's talk about ruling out closed orbits. Okay, so there's a few different situations where we can say for sure that we don't have any limit cycles or any periodic solution in general. So first situation is if we have what's called a gradient system. Okay, so in a gradient system, takes the form x dot is equal to negative gradient of v, where v is just a single valued function of only position. Okay. And so in a gradient system, we can never have a closed orbit because if we were to have a closed orbit, then essentially the integral from 0 to say the period of that closed orbit when it returns to the initial condition after time tau here, the integral of v dot dt, well, this is simply by the fundamental theorem of calculus, v of tau minus v of 0. And essentially, since we know that at time tau we've returned to our initial position and v is a single valued function of only position, then this integral will be identically 0. Okay. However, let's expand v dot. Okay, so dv over dt is precisely the gradient of v dot with x dot plus the partial of v with respect to time. And since v is a single valued function of position, it has no explicit time dependence, and so this partial derivative goes to 0. And so we simply have that v dot is gradient of v dot x dot. So we're going to have integral from 0 to tau of gradient of v dot x dot dt. And then plugging in for a differential equation, we have gradient of v is just negative x dot. So this is just integral from 0 to tau of negative x dot squared dt. Okay, and now since we've assumed that we're not at a fixed point, right? We're dealing with a closed trajectory that actually moves with time. This term has to be non-zero, and so because of that, we get something that's strictly less than 0. Okay. And so this is a contradiction, and it basically proves that in a gradient system, we can never have a closed orbit. Okay, so let's give an example of a gradient system, okay, just so we can see this process. So an example of a gradient system they give here is x dot is equal to sine of y, and y dot is equal to x cosine of y. Okay. So to find whether or not a system is a gradient system, we're just going to set the gradient of v, negative gradient of v, equal to x dot y dot. Okay, and so we know that v sub x should equal x dot, and or negative v sub x, and negative v sub y should equal y dot. Okay, so let's go ahead and solve for this first equation here. So we know that sine of y is equal to negative v sub x. So I'm just going to integrate both sides with respect to x here, and I'm going to solve that v. Wow, slow computer. So v is equal to the integral of negative sine of y dx. This is just negative x sine y plus some constant, and this constant is a function of y, right? Because we've only taken the partial with respect to x here. And now I'm going to take what I've just solved for v, and I'm going to take the partial derivative with respect to y. So I get partial with respect to y is negative x cosine of y plus c prime of y. And now I'm going to set this equal to negative y dot. Okay, and so y dot is x cosine of y, so we get negative x cosine of y. And this works out really nicely, and we just say c prime of y is identically 0. So this means just c of y is just some constant c. Okay, and so now we can see that by constructing this gradient function, we know that v is simply negative x sine of y, and we can add a constant if we want, but we don't need to. So this is the gradient function, and taking its gradient, we actually get precisely this relationship holds. And so we know this is a gradient system, and therefore it can't have any closed orbits. Okay, and now the whole idea of this is like, why doesn't this work for everything? Well, these equations basically have to match up. So this solution method that I just showed you of how to solve for the gradient, where essentially you start with the first equation, you solve for v, and you get like an arbitrary constant function in terms of y, and then you differentiate v with respect to y and set it equal to the second equation. This method will either contradict itself, so it'll prove that it's impossible to actually construct the gradient because you're going to have like certain terms that just can never match up, or um, you're actually going to be able to construct the gradient explicitly, and then therefore rule out the closed orbits. Okay, so this is how this method works. Now, another way to rule out closed orbits is what's called Lyapunov functions. And these are a lot more difficult to find in general, okay? There's no like straightforward method for constructing them like what I just showed you for the gradient. But what a Lyapunov function is, a Lyapunov function is essentially a function v that's continuously differentiable and real valued that satisfies these certain properties. So the first property is that v of x is going to be strictly positive for all x not equal to some key point x star, and then v of x star is equal to 0. And this is called positive definite. And then the second property is that v dot is strictly less than 0 for all x not equal to x star. Okay. And so this has kind of the same idea for ruling out closed orbits as the gradient, but it's less like direct. It's less like a direct relationship between x dot and v. Okay, but the whole idea is that kind of we have this almost potential or Lyapunov function v that's always decreasing along trajectories. Okay, so any trajectory that starts in space will always tend, since v dot is strictly less than 0, it will always move towards the minima of v, which is 0 at the point x star. And so any closed orbit would be impossible because it would require that v would remain invariant along that closed orbit, i.e. the integral from 0 to tau of v dot dt would have to be 0 along a closed orbit, but this is impossible because v dot is strictly negative. And so because of this, we can say that essentially all trajectories will approach this x star, and x star is in fact a globally stable fixed point, okay? And so these are a lot less obvious for how to construct. There's no straightforward method to do it. It's kind of through guess and check, or what the author claims to be divine inspiration, which I would definitely agree with. So we have one example that he gives is the system x dot is equal to negative x plus 4y, and y dot is equal to negative x minus y cubed, okay? And so now we're going to choose v of xy to be a sum of squares, so x squared plus ay squared. So observe that v has this nice property that essentially it's always going to be positive, and it's always going to be strictly. We need to show that it's strictly decreasing. Okay, so we immediately get that v of x is greater than 0 for all x not equal to 0. Okay, and now we're essentially going to show that this sum of squares, we can, for some choice of this parameter a, we can show that v dot is strictly negative, okay? So let's calculate v dot. We get 2x x dot plus a 2ay y dot. Okay, and now I'm essentially going to plug in for x and y dot here. So I'm going to get 2x times negative x minus plus 4y, and then plus 2ay times negative x minus y cubed. All right, and so I'm going to get negative 2x squared plus 8xy plus 2a negative xy minus 2ay to the fourth, okay? So as long as a is positive, we know that these two terms have to be strictly negative for a non-zero vector. And then all we need to do is choose a such that these terms cancel out and go to 0. So kind of grouping these terms, we have xy times 8 minus 2a, okay? And so the clear choice of a here is a is equal to 4, okay? So when we choose a equals 4, then this term goes to 0, and we simply get that v dot is equal to negative 2x squared minus 8y to the fourth, and this is strictly less than 0 for all x not equal to the 0 vector. Okay, so this is an example of something we've shown to be a Lyapunov function. Okay, so let's just recall this was the original function. That's the Lyapunov function, and it's nice that it's a sum of squares because we immediately get that it's a strictly positive definite function. Okay, and this is kind of a common choice, actually, is the sum of squares. There's a few other choices that he mentions for Lyapunov functions. Okay, so he says actually he says sums of squares are the only example that he directly gives, but usually you need to kind of have some experience with the nature of these two equations and kind of get a sense for what function might what function could you choose such that it's positive definite and its derivative strictly negative. And this parameterization is a really nice trick to give you some freedom to kind of manipulate the equations and try to force v dot to be strictly negative. But like he says, this is an extremely difficult thing to do in general unless you have like a good sense or a good feel of what's the right function to choose. Okay, so the next way to rule out closed orbits, and the final kind of strategy that we'll go over, is called Dulac's criterion. And this is a property that relies on Green's theorem that essentially says that if we have a system x dot is equal to f of x, and we can find some continuously differentiable real valued function g of x, so I'm just going to put g is within C1 of R, okay? It's kind of a shorthand notation for continuously differentiable real valued function. Then if we have such that the gradient dot gx dot, okay, has one sign, okay, so it's either strictly positive or strictly negative, then no closed orbits can exist. And specifically, I should state that this theorem can be applied to any kind of domain or simply connected subset of the plane R. So if we are operating in any subset, any simply connected subset R, R, which is a subset of the plane, then essentially, if this function g, which is continuously differentiable real valued, if its gradient dot product with gx dot has one sign throughout that region or that subset, then no periodic or closed orbits can exist within this region R. Okay, and the proof of this is essentially as follows. So it uses Green's theorem. So if we have that by Green's theorem, the integral over this a defined by the region R. So here's the region R, and then here is our a. Okay, and so suppose that there were a closed orbit along the boundary here, and R is totally arbitrary, so we can consider R to be the interior of any closed orbit, okay, of the gradient dot product with g of x dot dA. This is equal to the line integral along the boundary of a of g of x dot with n ds. Okay, and so due to the fact that this expression has one sign, okay, and it's strictly either positive or negative, this left hand side here can never equal 0. But if we're dealing with the interior of a closed orbit, then along this closed orbit, x dot has to be tangent to the orbit at all times, and therefore x dot dot product with the normal vector to the orbit is always going to be 0, because the tangent vector will be x dot, and the normal vector will always be orthogonal to the tangent vector, and so this will be identically 0. And so we get kind of that this equality by Green's theorem can never actually hold if C were a closed orbit, and therefore we can rule out closed orbits with this function g. Okay, and he says that the problem with Dulac's criterion is similar to the problem with the Lyapunov function. It's that it's extremely hard to find a function that can actually satisfy this criteria. Okay, and in this case, he says that there's a few trial kind of functions that might work, like 1 over x to the a, y to the b, e to the ax, and e to the ay. And I'll quickly do an example just to show you all how this might work. So the example he gives is he has x dot is equal to 2x times 2 minus x minus y, and then y dot is equal to y times 4x minus x squared minus 3. And we're trying to show that this equation has no closed orbits. This differential equation has no closed orbits in the positive quadrant, x, y strictly greater than 0. And this is a relevant model, and we can kind of look at this model and get a sense of what it might be trying to approximate. And for me, when I look at this system, I immediately get the feel of like a population dynamic, okay, where essentially this would be like our growth rate here, and then we have like a carrying capacity coefficient here, and then we have some sort of competitive like competition between the two populations with this y term. And so this might be like a predator-prey population model, but that's just pure speculation. Anyways, let's go into the Duloc's criterion for this. So to do Duloc's criterion, we first need to choose G, and it's kind of just given to us. We're like, okay, well, a hunch tells us to pick G is equal to 1 over xy. And so we do, and we're going to get that the gradient of gx dot, this is equal to partial over partial x of gx dot. Okay, just write it out. Plus partial over partial y of gy dot. Okay, and so the nice thing is that when we plug in for x dot and for y dot, these terms, the x and the y, are going to nicely cancel, as you'll see. So I'm going to go ahead and plug in the equations for x dot and y dot, and I'm going to get partial over partial x of 2 minus x minus y over y minus partial over partial y of 4x squared, at 4x minus x squared minus 3 all over x. Okay. And so this is a very nice kind of substitution because we've automatically gotten rid of the y dependence of y dot by our choice of g. And so this term just goes to 0. And we're left with just the only term that's going to stay in here is this x is the negative 1 over y with coefficient of x. So we're going to get negative 1 over y. And this is strictly less than 0 in the positive quadrant. Okay, so in quadrant 1. And there you go. That's our g function. And by Duloc's criterion, we can rule out closed orbits. Okay. All right. So these are all the methods that he outlines for ruling out closed orbits. And now let's talk about how we might prove that a closed orbit must exist in a system. Okay. And so there's only one kind of theorem that he mentioned in this book, and he says that there are very few ways for actually showing that a closed orbit does exist. And this theorem, called the Poincare-Bendixson theorem, is one of the greatest kind of tools that we have to work with. So Poincare-Bendixson theorem. Okay, so it basically states that if we have R is a closed bounded subset of the plane, and x dot equals f of x is continuously differentiable vector field on an open set containing R. So I'm just going to say f is within C1 of R. R2, I should say. And then the key criterions, okay, so R does not contain any fixed points. And then secondly, their trajectories are confined to R. So once a trajectory starts in R, it must stay there for all time. If we can show that these two conditions hold, then essentially we know the result of the theorem says that then there exists a closed orbit um, in R. And in fact, that closed orbit is attracting, so all trajectories will approach this closed orbit. So I should put stable. All right. So let's kind of draw a picture of what's happening here for the Poincare-Bendixson theorem. So we have some region R of phase space. And we basically prove that, first of all, there's no fixed points in this region R. And second of all, any trajectory that starts in here has to stay in here for all time. And I drew this horribly. That could never happen. Say I have something like this. It has to stay in here for all time. Then eventually it has to approach some closed orbit. And it can't approach a fixed point because there's no fixed points in here. Okay? And so one way to show that the trajectories are essentially trapped in R is to show that along the boundary of R, the vector field always points inward. Okay. And if we can show that, then we've constructed what they call a trapping region, and basically proved that R acts like a trap and that no trajectories can ever escape the walls or the boundaries. And then we can basically apply the Poincare-Bendixson theorem to state for certain that there is indeed a closed orbit within R. Okay, so let's go over an example of this idea. And there's a lot of excellent kind of examples in this book that you should check out. But I'm going to go through what the example that I find to be the most relevant and useful. Okay, so over here. All right, so this is a model of glycolysis, and it's essentially a model of two concentrations of certain chemicals. We have ADP and F6P, fructose 6 phosphate. Okay, and we basically are modeling their concentrations during glycolysis with this differential equation. So we have x dot is equal to negative x plus ay plus x squared y, and y dot is equal to b minus ay minus x squared y. Okay, awesome. So the way that we approach kind of solving this system and showing that there are closed orbits, or what choices of parameters of b and a in fact necessitate there to be closed orbits. Okay, so we're first going to sketch the null lines. And so the null lines, just to remind you, occur when I set x dot identically equal to 0. And then that'll be the first null line. And then the second null line, I'll do it in a different color. We're going to set y dot identically equal to 0. Okay, so let's draw out our phase plane here. And then essentially, we're only really going to consider the first quadrant because this is a physical system. And for this physical system, we know that these quantities have to be greater than 0. So the first null line, I'll just sketch for you here. So the first null line looks like this. So it looks something like this. The second null line looks like this. Okay, and so this is this one is y dot is equal to 0. The other null line is x dot is equal to 0. And then, as you might remember, any intersection of two null lines is a fixed point. So we know that this intersection here is a fixed point of our system. It's something to always keep in mind, okay? And so essentially, what we can show is that doing a bunch of doing a bunch of algebraic analysis, we can see that when x is equal, this computer is so slow. All right, so we're going to do an example of constructing a trapping region to prove the existence of a stable limit cycle. Now recall that stable limit cycles that are isolated are very, very important for dynamical systems in science and in like worldly studies, because it's very common that in biology or chemistry we'll have a sustained oscillation. So essentially we'll have some oscillation that's intrinsic to the system itself, and that oscillation is sustained. So if you perturb like the system slightly, the parameters of the system, eventually the system will settle back into that sustained oscillation. Okay, and so in this example in the textbook, we're given this system of equations here, which represents the concentration, X represents ADP and Y represents F6P of certain chemicals in glycolysis. Okay, we want to show whether or not there is a stable limit cycle, and for what parameters A and B this limit cycle exists. Okay, so the first step here is to draw the null lines of the system. And the null lines are basically found by setting x dot and y dot equal to 0, as I've done here already. So as you can see, I went ahead and set x dot equal to 0 and solved for y here. And then I set y dot equal to 0 and solved for y in terms of x. Okay, so we get two equations, and those represent null lines in the phase plane. Okay, so I've drawn these out here. So along these null lines, along the blue null line here, we can only have vertical flow because x dot is identically 0, and along the pink null line, we only have horizontal flow because y dot is equal to 0. Now, two little points I want to make here is that this intersection point here is actually a fixed point, right? Because of the fact that when x dot and y dot are both equal to 0, we have no flow at all. So we do have, by definition, a fixed point there. And that intersection point occurs precisely at x equals b, because by observing these two equations, these null lines clearly intersect. If you just kind of glance at them, they're going to intersect exactly when x equals b due to the symmetry of the two equations. Okay. All right. So now let's kind of jump into this. So the next step is to determine the direction of flow along these null lines. Okay, so essentially we're going to partition this plane into four sections, which is kind of separated by the null lines, and we're going to determine the direction of the flow along those four sections. So I'm going to start with the blue x dot null line here, and I'm going to start looking at this first region to the left of x equals b. So along that region, if I just quickly look at the x dot equation here, if I have this y is equal to, let's see, x over a plus x squared. Okay, so if I plug in this value for y along this null line into my equation for y dot, I'm going to get that y dot is precisely b minus x. Okay, so when x is less than b, then this flow, that y dot is going to be positive, so I'm going to have upward vertical flow along this null line. And then when x is greater than b, of course, then y dot is going to become negative, and x dot is still 0, right? So since y dot is negative, we're going to have this downward vertical flow. All right, and I'm going to go ahead and do the same thing for y dot here. So, okay, sorry. So for y dot, we have plugging in y dot is equal to 0, we have y is equal to b over x squared plus a. And now if I plug this into the equation for x dot, I'm going to get b minus x again, right? So I'm actually going to get the same thing. And so here I'm going to have x dot is positive when x is less than b. So I'm going to have flow to the right, positive flow to the right. And then when x becomes greater than b, x dot becomes negative, right? B minus x becomes negative, and so we're going to have leftward negative flow in the x direction. Okay, and so now based on this flow along the null lines, it turns out that that I can exactly identify kind of the general direction of flow in each section of the phase plane that's separated by the null lines. And let me explain to you why. So first of all, I know that in this section here, I'm going to have flow that's upward and to the right. And that's simply because um, every trajectory that stays to the left of this pink null line, okay, essentially means that y dot cannot change sign, because this null line, this pink null line, represents when y dot is equal to 0. So it represents the moment at which y dot changes sign. And so to the left of this null line, since we've already identified y dot is positive in this region, it's always going to be positive to the left of the null line. Okay. And similarly, above this blue null line, we know that the flow will always be to the right, because in order for the horizontal direction of flow to change direction, it would need to hit the value 0 in order to change sign, and so it would have to actually cross this blue null line. Okay, so this is the precise reason why these null lines nicely separate the plane into different regions of flow. Okay, and so I'm going to quickly kind of observe here, and I can see the general directions of flow in all of these different areas. Okay, so like this. And so we see that we do have kind of an oscillatory looking flow, but that's not sufficient to really prove that we have a stable oscillation, because we could just have spirals, right? Specifically spirals into the into the fixed point there if it were stable or unstable. Okay. And so we needed to do further. We need to construct a trapping region. So the first thing I'm going to recognize is that as long as x is greater than b, this blue null line, okay, is always going to be above the pink null line, okay? And that's simply due to these equations here. If when x is greater than b, this value of the null line given in blue is always going to be greater than the one in pink, okay? And so that means that essentially along the x-axis, I'm always still going to have upward flow, okay? Because I'm below this pink null line. And so I'm actually going to have upward flow along the x-axis like this, okay? Which is good for us because we want to start trying to build a trapping region where all of the flows go into that trapping region. So I'm going to use the x-axis to start building my trapping region, because I know that all the flows are going to go into a like they're going to be in the positive y direction along the x-axis. Okay. And now similarly along the y-axis, we also have the same behavior, because we're always going to be above this blue null line, and so flow will always be to the right. And so I know that I'm going to have flow to the right of the y-axis, and so I'm going to use the y-axis also in my trapping region here. Okay. And now I have upward flow. Sorry, as long as I'm hold on, let me think of this. Yeah, so as long as I'm above this pink null line here, I'm actually going to have downward flow, right? So everything in this region flows in the negative y direction. All right. And so I'm going to extend my trapping region out to x equals b here, all right? Because I know that the flow is going to be to the right and negative. Okay, so something like this. But now I have a problem, because if I just want to make a box here, that's my trapping region. When I try to connect this edge of the box, okay, the final vertical edge here, I'm going to get flow that goes out of the box. And so the box will no longer be a trapping region. Okay. So there's a trick here. And the trick is to actually use like a diagonal line here given with a slope of -1. Okay. So a diagonal line starting at x equals b. And the reason why is because if we look at, for large enough values of x, okay, you can see that x dot and y dot are governed by these two terms here. And these two terms are essentially going to mean that x dot is going to be approximately equal to negative y dot because they're equal in magnitude. And so now I just want to compare the actual values of x dot and negative y dot. Okay, and if negative y dot is greater in magnitude than x dot, that means that I'm going to have flows that go down more vertically than they do horizontally. And so they're going to be actually fall into this trapping region. Okay. And so if we look at this, if we compare these equations, what we see that this precisely occurs. X dot is less than the magnitude of y dot precisely when x is greater than b. Okay. So when x is greater than b, then we have that essentially this term is still going to be positive, but this negative x term is going to be more destructive. And so we're going to have a system that ultimately has a smaller magnitude of flow in the horizontal direction than in the vertical direction. And so along this diagonal here, we're going to have flow that goes into the region. Okay. And so now we've determined that this region I've drawn here in blue is indeed a trapping region. So is that sufficient to show that a stable limit cycle exists? And it turns out, no, it's not, because we still have a fixed point. So remember, the trapping region can't contain any fixed points. So the final idea is to show that for some values of A and B, this fixed point becomes unstable. And then once it becomes unstable, we can kind of punch out a little hole around it. And we know that all trajectories are going to flow out of it since it's unstable. And so then if all the trajectories are flowing out of this unstable fixed point, then the region formed by this kind of trapezoid rhombus looking figure and this punctured hole will sufficiently constitute a trapping region. And then we'll have a stable limit cycle guaranteed by the Poincare-Bendixson theorem. Okay, so let's go ahead and do this. And to determine the stability of the fixed point, all we're going to need to do is take the Jacobian. Okay, and so if I want to linearize the system, well, I can see that it's nonlinear and its linear terms are pretty clearly separated already. Okay, so if I linearize this system, I'm going to have that. Let's see, we're going to have partial f over partial x, partial f over partial y, partial x, partial g, partial y. All right, so let's go ahead and get into this. It isn't going to be as easy as I thought, but we'll get through it. So I'm just going to find the Jacobian. Okay, so that the Jacobian is just the essentially the derivatives of the system of equation, the partial derivatives with respect to each of the independent variables. Okay, so the first entry of the Jacobian is going to be the partial derivative of the first equation with respect to the first variable x. So I have -1 plus 2xy. And then partial f over partial y is going to be a plus x squared. Partial g over partial x is precisely -2xy. And then partial g over partial y is negative a plus x squared. All right. And so when we have at our fixed point, we have precisely x equals b and y equals b over a plus b squared. You can plug that into either one of these two null line equations to give you the coordinates of the fixed point. And so now, unfortunately, I'm just going to have to plug this in and chug this here. So before I plug everything in, I'm going to go ahead and look at this determinant of the Jacobian and the trace. Okay, so the determinant of the Jacobian, I'm going to have 2xy minus 1 times a plus x squared minus plus 2xy plus squared. Okay. Hoping it'd be a bit easier than that, but wait, just 1 second. Hopefully you caught this mistake, but I was too quick to assume this is a trapping region. We still have one last little area to determine the flow, and that's when it intersects this blue null line before it intersects the x-axis. So since the blue null line is positive, it will intersect it before it intersects the x-axis. And finally, we can just draw a vertical line down to the x-axis from there, because once we cross the blue null line, the flow starts to move in the negative x direction. So we get leftward flow. And so along this vertical line, we do have flow into the region as well. Okay, so this is our trapping region. It's kind of a weird pentagonal looking figure. And we've shown that across all of these lines in this closed region, across all of its boundary, the flows of the vector field governed by the differential equations are inward to the trapping region. So the last step is to show that there are no fixed points. Well, that's a problem because we do have a fixed point, right? The fixed point is the intersection of the two null lines right there. However, if for some values of a and b, this fixed point were to become unstable, then we could just puncture a little hole in our trapping region, which I've drawn here in pink. And then since it's an unstable fixed point, all of the flows in its local vicinity will have to flow outward away from it. And so then the trapping region given by this pentagonal blue shape that I've given here, combined with the small punctured hole around the fixed point, will indeed be a trapping region and will guarantee the existence of some closed orbit, stable closed orbit. Okay. And so now let's show for the specific conditions of A and B such that this fixed point becomes unstable. So first of all, let's explicitly determine the coordinates of the fixed point. Okay, and I've done that here. So we know x equals b, and then the last thing is I just plugged in x equals b to the equations of the null lines, and we get y is equal to b over a plus b squared. So now I'm going to take the Jacobian of our system here and plug in and evaluate that Jacobian at the fixed point. Okay. So remember, if you remember, the Jacobian is just partial f over partial x, partial f over partial y, partial g over partial x, partial g over partial y. Okay, and so this is a local linearization of the system. And so I'm going to go ahead and take these partial derivatives, take the derivative of x dot with respect to x, and we're going to get -1 plus 2xy, and then a plus y squared is the partial derivative of f with respect to y. Here we have -2xy, and partial g, partial y is going to be -a plus x squared. Okay, and so now I'm going to want to take the determinant of this thing and the trace, and then plug in the values of the fixed point. Okay, so the determinant is going to be, we're going to have 2xy minus 1 times -a plus x squared, and then minus plus 2xy times a plus, this should be an x squared, I'm sorry, a plus x squared. Pretty sure I just did the differentiation wrong. Yeah, okay. So 2xy times a plus x squared. All right, and now this is looking pretty nice because these 2xy terms are going to cancel out. So I'm just going to get an a plus x squared. So I can see that my determinant is actually always positive because we're assuming these parameters are positive. By the way, generally speaking, if you have a system with some parameters, the signs of that system will generally be given so that the parameters are non-negative, okay? Not always true, but that's like kind of a convention. All right, and so we didn't know that the determinant is positive, so now we just need to evaluate the sign of the trace, and we need to show when the trace becomes positive, because that's going to give us our unstable fixed point, okay? So let's look at the trace here, and the trace is precisely, it's going to be 2xy minus 1 plus minus a minus x squared, okay? All right, and let's go ahead and plug in the fixed point, the values of x and y, okay? So we know that xy is precisely going to be 2b squared over a plus b squared minus 1 plus minus a, and then x squared is going to be a b squared, so minus b squared. All right, and so now I'm going to do some algebra here. So let's see. We have 2b squared minus a plus b squared. And then this is a minus a plus b squared. So we're going to have a minus a plus b squared all over a plus b squared. And the algebra is just kind of gross. I almost want to spare you from it, but I'm going to keep going. B squared minus a plus b to the fourth negative minus b to the fourth plus 2ab squared plus a squared. And then times a plus b squared inverse. Okay, so we really care about the sign of the numerator here because the denominator is always going to be positive. And so if we just look at this numerator, we want to find roots of this equation and essentially find when it's negative and positive. Okay, and so I just it's still kind of gross, honestly. Let's see what the book says. Yeah, so essentially we're just going to solve for b squared. We're going to solve for the roots of this equation by solving for b squared in terms of a. Okay, so we have b squared squared. And yeah, I'm going to set this equal to 0. So b squared squared plus 2a minus 1 b squared. Plus man, my algebra's rusty. Okay, so essentially we have a quadratic equation in terms of b, and yeah, I'm going to stop the video right here. And somehow I actually did do the algebra properly, and this is the correct equation for b squared. And so if we plug this into the quadratic formula to solve for the roots when this is 0, all right, we're going to get that b squared is equal to 1/2 1 minus 2a plus or minus the square root of 1 minus 8a. And I'm just copying that from the book because I don't want to go into the algebra right now. It's just plugging things into the quadratic formula. And I'm going to trust that Stephen Strogatz knows his quadratic formula. Okay. And here there's an important note, which is that, this equation is going to give us certain regions of parameter space where this term is positive and negative. And we have to be careful because this equation that I set up is actually the negative version of this piece here, okay? But essentially, we divide the region of A and B based on this equation into kind of two regions like this, okay? And here in this region, in this blank region here, we have that the fixed point is stable, so the trace is going to be negative here, and then here the trace is positive. And where the trace is positive, we know that the fixed point becomes unstable, and so therefore, since we've constructed the trapping region, let's go back to our system here. So when the trace is positive, whoa, here, trace is positive, we have an unstable fixed point, and so the flow is going to be outward, and so we've constructed a trapping region by just puncturing a microscopic hole around the fixed point of arbitrarily small radius. And therefore, we've constructed a trapping region, and so we apply the Poincare-Bendixson theorem, and we have proven the existence of a stable limit cycle. And then glycolysis occurs as hoped for, and the chemical reaction has this sustained oscillation, and we get to live, and biology works. So yeah, obviously this is a super simplified version of real life systems, and the real question is, do these differential equations, are they accurate models of reality, or how useful are they in modeling scientific systems? And it turns out that they're really, really useful, not only in just predicting and describing phenomena, but also in like understanding kind of, if you believe, like I believe, that math actually plays a role in the way that biological systems work. Doing this will give us a qualitative understanding of like how changing certain parameters of a system can actually result in things like a sustained oscillation. And this is really important in engineering, physics, and biology, especially when these parameters are either changing due to the environment, or we have control over them and can change them at our own will. In both scenarios, we want to kind of be able to predict the effect of parameter drift. Okay. All right. So this chapter has a bit more stuff on something called two timing, and it's essentially going into estimating the period of these sustained oscillations. And so I'm going to go through that with you right now. Okay, so the last thing we're going to talk about this chapter is something called two timing. All right, and so if we look at a differential equation, specifically an oscillator, okay, or something with oscillatory solutions, we have like the classic example of a like linear resonator, okay, or a damped harmonic oscillator, and essentially we're going to look in the limit of weakly damped. Okay, so this 2 epsilon term, epsilon is going to be very, very small. Okay, so in the limit of a weakly damped oscillator, okay, we want to kind of examine methods for estimating the period and shape of oscillations. Okay, specifically the period. And the way that the author tells us to do this is with a method called two timing. So originally, you might think that the best way to like approximate, and we know the solution to this. Okay, first of all, it's a linear equation, so you can solve for the characteristic equation and find the roots of the characteristic equation, and then use that to construct, a general solution. But I'm going to go ahead and give that to you. Okay, so that's like an ODE's kind of technique here, and we have 1 minus epsilon squared to the 1/2 e to the negative epsilon t sine of 1 minus to the 1/2 t. Okay, so this is the actual solution to this differential equation. All right, and how you get this is essentially you solve for r squared plus 2 epsilon r plus 1 is equal to 0. You solve for the roots of this equation, and you're going to get negative epsilon plus or minus the square root of 1 minus epsilon squared, if we are going to match up with this term. And so the 1 minus epsilon squared goes into the square root of 1 minus epsilon squared is going to be the frequency of the oscillations, and then this negative epsilon is precisely going to enter into the exponent here. Okay, so that'll be the damping coefficient. All right, but without using methods of ODEs, so pretend this is like a nonlinear equation and we don't have the methods to actually get the explicit solution, then one way you might think to do it is to use a Taylor series expansion in X. Okay, so if you plug in like X of t epsilon is equal to X naught of t plus epsilon x1, and x1 is also a function of t, plus epsilon squared x2 of t, etc. Okay, so if we expand this as a Taylor series in epsilon, and then we try to plug it into the differential equation and separate terms of equal order, so plugging this into the differential equation, we're going to get x naught double dot plus x naught plus epsilon times x1 double dot plus 2x naught dot. And this just comes from substituting this into the original differential equation here. Okay. And then plus order of epsilon squared. And then we just assume that since epsilon is small, we're dealing with a weakly damped oscillator. We can ignore these higher order terms. And then we want to view these terms separately. So we want to set this equal to 0 and separately the order. This is the order 1 equation. This is the order of epsilon equation. And we set them both identically equal to 0. Okay. However, the problem with this is that we're going to end up, if we actually do this, okay, we're going to get that x naught of t is going to be sine of t. If we assume that the initial conditions are like x0 of 0 equals 0, assuming that x0 of 0 equals 0 and x1 of 0 equals 0, okay? So the problem is that when I plug this x naught into this second order of epsilon equation, I get a resonant forcing term, because I immediately get, x1 double dot plus x1 is equal to negative 2 sine, or negative 2 cosine t. And this term, if you've studied ODEs, you'll know that it produces resonant forcing, because the frequency of this cosine is exactly the same as the frequency of the general solution. So then the particular solution is going to be of the form t times sine of t, basically, or some trigonometric function. Okay, and turns out the exact solution becomes literally negative t sine of t for x1. And so the problem is that these solutions aren't even damped. They're literally growing linearly with time. The envelope of the amplitude is growing. And so eventually this is going to totally misrepresent the behavior of the solution. And it actually will represent the behavior of the solution in a very short time frame. But then, if you solve for x naught and x1 and then plug it back into this equation, it will solve for the behavior of the system in a very short time frame when t is much, much less than epsilon. But then after that, you're going to quickly lose the accuracy of your solution. And in fact, it's going to completely misrepresent the behavior of the system, because this equation is exponentially decaying, whereas the solution that we just derived has, in this x1 term, it's growing linearly as t sine t. And so the problem is actually that we've solved for the first two terms of the Taylor series of this solution. And the Taylor series of this solution, because of this e to the negative epsilon t here, the Taylor series expansion is going to have like a 1 minus epsilon t here. You see that? And then this is going to be like multiplied by some trigonometric function. And so if I only take the first two terms of the Taylor series, I'm going to get like this linear term that's just going to that's just going to grow, okay? And so I would need to take infinite number of terms to get it to converge to this exponential decay function. If I only take two terms, I'm only going to get a linear approximation, and it might be good for a while, but then eventually it's just going to start growing, and this t term will start dominating, and we're going to totally misrepresent the behavior. So clearly this is a huge problem. And it's all due to the resonant forcing. When I start to try and separate, x naught and x1, I get these coupled equations that end up causing resonance terms, okay? And so the method of two timing essentially deals with this problem by creating a method of substitution that eliminates resonance, okay? And so what you do is, let's go back to our equation here. All right, so I'm now going to have two time scales, okay? So, and the basic idea of two timing is this. So if we have like the general solution that behaves something like this, okay? So we have the time scale on which the short time scale t, on which the sine wave is going through a full oscillation, and then we have a longer time scale tau, where we actually can observe a decay in amplitude, okay? So we're basically assuming that the decay in amplitude is occurring on a different time scale than the oscillations in the frequency of the sine function, okay? And so by making this assumption, I'm gonna choose two time values. So I'm gonna choose t, which is just equal to time, and then I'm gonna choose capital T, which is gonna be epsilon times t. Okay. And so essentially, this is gonna be my fast time, and this is gonna be my slow time, because it's gonna grow much more slowly with respect to time. Okay. All right. And the key is I'm gonna treat these as independent variables. So essentially, I'm going to assume that the function's dependence on little t is totally different from its dependence on capital T. And so this is the same kind of assumption that certain characteristics only happen in long time frames and certain characteristics only happen in short time frames. For example, this might be like assuming that a person's height stays constant within the frame of a day, whereas over the frame of a few years, a person's height is going to drastically change. And so I'm actually going to treat that day and the year timescales as independent of each other, all right? Which is obviously an approximation, because the longer timescales are just built by the like closer timescales, and without the closer timescales, you wouldn't have long timescales. So this is an approximation, and it's not really clear why it works so well, but it does. And so let's go into this. So I'm going to expand the solution x of t epsilon as precisely x0 of t and then tau. So tau, like this capital T, is a totally new parameter of the system, plus epsilon x1 of xt tau, okay, plus epsilon squared of x1 t tau. Okay. And now, same as before, I'm going to plug this in to the differential equation. But here's the trick. So essentially, I'm going to take the full time derivative of each of these functions. So the full time derivative of, for example, x naught with respect to time is going to be the partial of x naught with respect to time plus the partial of x naught with respect to tau, partial tau with respect to time. Okay. And so I'm going to end up getting the partial of x naught with respect to little t plus this term becomes an epsilon plus epsilon partial of capital T x naught. Okay. So hopefully that makes sense. It's just an expansion of the full derivative of x naught with respect to time. And so with this in mind, I'm now going to go ahead and plug this x of t epsilon into our equation here. And so I'm going to get, let's see here. So going to get partial t plus epsilon partial tau squared of x. Oh yeah, this is kind of gross. Okay, I'm going to do this and then come back. Okay, so after doing the math, I've essentially just started with an equation of x that's a power series expansion in epsilon. And now I just take this derivative, which is the full time derivative, okay? And so expanding in terms of the partials, it's equal to the partial with respect to small time plus epsilon times the partial with respect to big time. And I'm going to take this full time derivative of this power series expansion in x, and I'm going to group terms in their order of epsilon, okay? So I've done this here for x dot. You can see that my order 1 terms, I just have the partial with respect to fast time of x naught. And then the order epsilon, I have partial with capital T of x naught plus partial of little t of x1 plus order epsilon squared. And then x double dot, I'm going to do the same thing. So I'm just going to apply that operator to x dot, applying this operator in blue here, to x dot to give me x double dot. And again, I've grouped the order epsilon and the order 1 and the order epsilon squared terms, okay? And of course, I'm just neglecting order epsilon squared because I'm assuming it to be negligibly small. All right, so now let's remind us of our differential equation. We have x double dot plus 2 epsilon x dot plus x is equal to 0, okay? And so now I'm just going to plug in what I know and group terms in order of epsilon. So x double dot, I'm going to have my order 1 terms is just going to be partial, double partial with respect to small time of x naught. Now I'm just going to look for other order 1 terms. So other order 1 terms will everything in this second term is at least order epsilon because we have an epsilon coefficient. So then I just look for x itself. And x itself has just x naught as a order 1 term, okay? All right, now I'm going to look at my order epsilon terms. So my order epsilon terms in x double dot is just going to be 2 partial t tau of x naught plus partial t x1. Okay, and then I'm going to add, let's see, so an epsilon here, there should be a 2 epsilon. Sorry, think about this. So yeah, okay. So the first order epsilon term comes from the x double dot, and it's just this term here. Okay, then now the second order epsilon term comes from this single x dot, and we're going to have 2 epsilon times 2 epsilon times x dot, and so the order epsilon terms are going to be the order 1 terms in x dot, right? Because they're going to get multiplied by 2 epsilon. So I'm just going to have a plus 2 partial t of x naught. And then finally, the order epsilon in the original x is just x1. And then everything else is order epsilon squared, okay? So this is what I get when I plug in the values of x, x dot, and x double dot into my differential equation, into my oscillator, my weakly damped oscillator. Okay, and finally, let me make sure this is correct. So yeah, this is right. Okay, so the next step in this process is to again treat these order epsilon and order 1 terms separately and set them both identically equal to 0. It's like if I have an equation a plus bx plus cx squared is identically equal to 0, then I essentially can group, I can say that a has to be 0, b has to be 0, and c has to be 0, right? And we're doing the same thing here in order of epsilon. So the first equation, I just have x naught double dot plus x naught is equal to 0. Okay, and that's the order 1 equation here. And I immediately know the solution to this, right? we have x naught is equal to, we're just going to have sines and cosines here. And if we assume, let's assume some initial conditions here that x of 0 is just 0. So we're going to assume that x of 0 is 0 and x dot of 0 is 1. Interesting. Okay. All right. So if x of 0 is 0, then okay, I'm just going to write this out. So sine of x plus b cosine of x. I'm going to plug in the initial condition and recognize that that essentially, let's see, sine, the b goes to 0. So it's just going to be a sine of x, and then the amplitude is going to have to be 1, 2. So yeah, using these initial conditions, I can solve for x not explicitly, and I just should get just sine of x. Let's make sure about this. Okay, so setting the order 1 equation equal to 0, we're going to observe that it looks like a first order, just regular ODE, but in fact it's a PDE, because we're assuming that x naught, remember we're assuming that x naught is a function of t and capital T, the two different time scales. Remember that's the fast time scale is the small t, slow time scale is capital T. And also I'm just going to write it here before I forget. We have initial conditions of x of 0 equal to 0 and x dot of 0 is equal to 1. Okay. So given this first order equation here, I know that the solution is going to be simply a cosine of t plus b sine of t. But now a and b are actually functions of capital of the other variable, okay, b of tau. And that's just due to the fact that, yeah, this x naught is no longer simply dependent on small t. We have dependence of the coefficients on the longer time scale, all right? And so this is our x naught, excuse me. And now I'm going to use that to solve for the order epsilon equation, okay? So this is the final step. I'm going to take my order epsilon equation, which is partial tt of x1 plus x1 is equal to negative 2 partial tau t x naught minus 2 partial t of x naught. Okay, so I'm going to plug in x naught into the right-hand side of this equation. This is my order epsilon equation. I'm going to plug in x naught into here. So I'm going to have negative 2, let's see here. So this is just going to be, this is actually going to become positive 2 a prime sine of t plus b prime minus b prime cosine of t. And then the second equation here is just going to be plus 2 a sine t minus b cosine t. All right, let's see if I got this correct. Yeah, okay. And so now the key point is this, is that if we look at the left-hand side of this equation, okay, this is, if we just look in terms of the small t time variable, we know that the solution is going to have cosine and sine waves of the form just sine of t and cosine t with a frequency of 1. And so all of these terms here on the right-hand side are going to cause resonance. So that's the key point of the two timing method, is that because these a's and this a prime is distinct from this a, because they're now functions of the long time scale, we can actually use that to manipulate a and b such that the resonant terms cancel with each other. Okay, so specifically we have that a prime, if we group the sine and cosine terms and cause their coefficients to go to 0 to destroy resonance, okay? We have A prime plus A is equal to 0, and B prime plus B is equal to 0. And so then we get A of tau is just E of negative tau, and times some constant. B of tau is B e to the negative tau. All right, and this is very nice. And so now we see that this prediction, immediately we can see that this is getting us somewhere, because if we compare to the general solution, we actually do have like an e to the negative, literally an e to the negative tau here. This is an e to the negative tau, because remember tau is epsilon t. And so because this 1 minus epsilon squared, the square root of 1 minus epsilon squared is close to 1, since epsilon is small, right? Like order of epsilon squared is very, very, very small. And so this frequency is approximately 1. And so we can immediately see that this two-timing method is going to give us a very good approximation of the solution, because we're going to end up with terms that are going to oscillate with a frequency of 1, and they're going to exponentially decay in the exact same way that that the real solution does. Okay, and so working out the equations for x naught, you get x naught is equal to e to the negative tau sine of little t, and then let's see, x. Yeah. So because x naught is because x is just x naught plus order epsilon terms, if we neglect the higher order terms, we just look at this x naught approximation here that we've gotten from two-timing, we can see that it is a very, very, very good approximation. Okay. Because, and in fact, it's like scarily good. It's like better than it should be. If we draw the real solution, something like this, then this two-timing solution looks pretty much identical, actually. It's like very, very close for small epsilon, okay? And that's because of what I already established, that the exponential, that in the real solution, we actually do have the same exponential decay that we've predicted using two-timing, and then the frequency is just slightly off, okay? The frequency is very, very close to 1, but it's order epsilon squared, which we've kind of neglected. And so if we wanted to take this into account, we would have to use three timings. We'd have to introduce a third, even slower time scale that was order epsilon squared. So might have to introduce this third time scale, which was epsilon squared t. Okay. Should it be epsilon t squared? Just want to get this right. Yeah, I got it right. Okay, awesome. So yeah, that's pretty much all I wanted to show you. Now, I only applied this to a linear equation, but it turns out the same method can apply to any nonlinear oscillator. So these coefficients in front of the x dot could be nonlinear, right? And the whole process is the exact same. So let's go through the process one more time just to review it. We set up a fast time and a slow time, and we choose them to be independent variables. And then we take the derivatives of x, the full time derivatives of x, using the partial derivative expansion, assuming that little t and big T are independent variables. Okay, and this will give us these equations every single time. Okay, and now we simply just substitute in these basically Taylor expansions of the 0th, 1st, and 2nd order derivatives. We substitute these into our differential equation. We group order 1 terms, order epsilon terms, and we neglect higher order terms. And then we set those equations identically equal to 0. And we solve for the order 1 equation first. And then once we get whatever we get for that solution, it's going to be something we can directly solve for more often than not. well, not more often than not, but it's going to be the easier equation to deal with. And so we solve for this equation, we solve for x naught, then we plug that into our order epsilon equation and solve for x1. And then the final key step here is that doing this, we're going to get two equations. We're going to have an order 1 system of differential equations, and then we're going to have an order 2 system of differential equations. And what we want to do is essentially set the coefficients of x naught such that the resonant terms in the order epsilon equation, those resonant terms, like the coefficients cancel out, and so they go to 0. So essentially, we're manipulating these coefficients of x naught so that the resonant terms cancel out and go to 0. And once we destroy the resonance terms, then our approximation will be much, much more effective, and it won't suffer from the same drawbacks as just like the plug and chug without using two timing, just using a single time Taylor expansion, can suffer from the drawback of, well, the terms, if you have like 2 or 3 terms in the Taylor expansion, eventually those are going to diverge away from the actual solution, simply because you're going to have like, polynomial, you're going to have like the resonance terms are going to produce polynomial coefficients of your sine and cosine waves, and those polynomial coefficients are eventually going to explode as time gets reasonably large. Okay, so that was a method of two timing, and I hope this helped. I'm getting back into the lecture. I'm definitely a bit rusty on this lecturing, but hopefully, I'm going to get back into it, and we're going to hopefully cover chapter 8 coming up soon here. Chapter 8 is bifurcations in the phase plane, so it should be quite interesting. All right. Have a great day.